All right, welcome everybody. It's great, fantastic to see so many language geeks around. And it's great to have a couple of language developers and designers here to grill. It's really nice because we have a language designer from academia that's doing kind of really crazy things with old languages. Then we have a practical language designer here that's kind of moved between types and dynamically typed, now doing JavaScript stuff. Then we have Mr. Supertype. Just Google the web for Scala and types, and like you see some kind of great things. And then we have Mr. Cotype.
The anti-type.
The anti-type, yes. So I think we have the right ingredients for a nice debate here. So let's start with Peter, because I think Peter is probably the least known of our panelists. And Peter, can you tell a little bit about yourself and what the problem is that you're trying to solve?
So my name is Peter Alvaro. I'm a PhD student at UC Berkeley in the database group.
By the way, UC Berkeley, best place for programming languages.
That's correct. I'm advised by Joe Hellerstein, so I'm not from a languages group, but our group has been playing around.
Well, I think you're doing languages, yeah.
Yeah, sure, why not? And I think the hard problem that we're facing now is the same hard problem that we've been facing for as long as there has been distribution, which is physical distribution. Not being able to globally see all of our state in one place and not being able to reason soundly about time when we're communicating with other agents. So that problem has always been there, and we actually understand what's hard about it pretty well. The problem has become much more urgent in recent times because of the advent of things like cloud computing, where the power of controlling a cluster and trying to orchestrate communication and computation across physically distributed machines has sort of fallen into the hands of Joe programmers like all of us. So it's the same hard problem that we're trying to solve, and we're trying to solve it with some of the same tools that have already existed. We're sort of looking at applying query languages like what you've seen in databases and logic programming languages to the problem of coordination in distributed systems. And we think that because the urgency of making distributed systems easier to program has blown up recently, we're going to be able to solve a lot of pain in the short term if our agenda is successful.
So why do you use logic programming? Didn't that die with the Japanese 5th generation project?
Well, actually, logic programming is something that has repeatedly died and been reincarnated, isn't that right? And we can expect to see this cycle continuing. I'm going to talk more about this in my talk tomorrow, but I think one really concrete advantage of logic programming is that it gets people thinking in terms of, first of all, operations over sets, which are implicitly partitionable and parallelizable and so forth. So you get a lot of sort of embarrassing free parallelism out of programming, expressing your computation in terms of transformation over data. The other thing is, if you're a Prolog or a Datalog geek, you're really superstitious about non-monotonicity because you're afraid of paradoxes in your logic program. And this translates into good distributed systems processes or techniques, because non-monotonicity in distributed systems where we have asynchronous communication is going to boil down to uncertainty about getting the same result in different runs, right? Non-determinism in execution. It's going to boil down to inconsistency of distributed state and replicas. And if you're interested in why, I can get into that now, or I can talk about it in more detail tomorrow.
Well, maybe you can explain to us what this non-monotonicity is. Is that something like, birds can fly, but now I have a penguin and it cannot fly, and now I'm confused? Or what is this?
How many people are database people in the audience? Not so many people. So, if you write programs in SQL, there's 3 operators that you use to do most of your heavy lifting. They're select, project, and join, right? Selection filters elements from a set. Projection selects some of the attributes of the tuple. And join is composition, right? It allows us to combine elements from other sets. All 3 of these operators have the property of monotonicity, which is to say, as my inputs grow, so also does my output. Another way of saying that is that if I make conclusions from these operators, those conclusions can be shipped off across failure boundaries to places where I can't retract them. They can be sent out in the form of missiles to other countries, and I don't have to worry about calling the missiles back home. Non-monotonic operators are those operators that don't have that property of outputs growing as inputs grow. Sort of the canonical example is set minus. Yeah.
So there is also a group by, right?
Group by.
Reduces the data.
Usually when we do a group by, we also call an aggregate function. An aggregate function is also non-monotonic because it's going to be, you're going to get data in the form, I give you a count, and then I ask for the count back, and I give you a new count. So although the canonical example of non-monotonicity is set minus or complement, aggregation in general is going to be non-monotonic as well. It's not good to have to recall missiles. So monotonic logic leads to pipelinable distributed systems.
Good.
If you write your programs in the right language, it's cheap and easy. Sometimes syntactic, it's just a syntactic matter to discover which portions of your code are monotonic and hence cheap asynchronous, or non-monotonic and hence must be guarded, might be blocking, you should be superstitious. So sort of the reason I brought this up is that if you're a data log programmer, you're already afraid of non-monotonicity for another reason, because non-monotonicity and cycles lead to paradox. Well, in distributed systems, we're less concerned with logical paradox, but we do care about being able to eagerly process the conclusions of our computation and ship them across failure boundaries to other agents.
So now to kind of jump from that to Martin, because I think, when I listen to your kind of thing, you're kind of a purist. Like, it's like everything is monotonic, so there's no side effects. That, that like I do my predicate and maybe kind of the next time I run it, I've set some global variable and now it's different. Now Martin has been kind of, doing interesting work in combining functional programming with imperative programming where, like these things are mixed together in a beautiful, nice soup. So can you say a little bit, and he's even started a company kind of, trying to sell this soup to, developers. So.
It's a cake.
It's a cake, okay.
Okay, so I think the challenge we try to solve is a challenge probably many people have here, and that's that we have to move from sequential programming to parallel, concurrent, distributed programming. And to do that with limited brain power, I think we have to shift from imperative programming to functional programming, because it's just too hard to keep shared state imperative programs honest in a parallel system. I mean, every time I try that, I screw up royally, and so I know how hard.
But look at me. I mean, I programmed Haskell when I was young,
right?
And this is the result. So I mean, do you really believe that functional programming is easier than imperative programming?
So the challenge I think we have, and you didn't have to the same degree. I think Haskell has this motto: avoid success at all costs. In Scala, we have a much harder problem, and that's actually getting hundreds of thousands of programmers that have been brought up with normal languages across the chasm.
But you agree that functional program is abnormal program, because you said imperative program is normal, or?
Oh, no, I said the normal state for a programmer until very recently and until today is to be a Java programmer or a C# programmer or a C# programmer. That's the standard thing. And actually C# also has already gone a fair bit towards this functional world. And I think Scala is just more radical in a sense in that to say to be really functional, I think you have to polish a lot of small parts of the language. So essentially the challenge is you should be able to write your program without a single var. And there are some syntactic things in Java and C# where even to pass parameters into a class, well, you have to declare a field. Well, then you can declare the field final, but it looks like an assignment. So these are sort of the things you have to get away. And the other thing you have to do is you have to get rid of statements and have an expression-oriented languages. And then, of course, the thing starts and you start polishing and polishing and polishing.
But don't you get at the limit to Haskell?
That's an interesting question, but I think very much no, because I think that the basic premise of object-oriented programming for composition with all its faults, it's still a sound one. So I think it's a big wheel that we're turning. That every time we say, well, let's just be all functional, and the pure functional programming in a sense is a lie, because you have a global namespace. I mean, Haskell is a global namespace for type classes. OCaml has a global namespace for variants and records. So that's, at some point, you see that's not scalable. We have to modularize somehow. And you start to do a module system, then you start to make your module system more dynamic and more flexible. Then, lo and behold, you have an object system. Then you overuse objects, and you say, well, all this inheritance stuff, it's just too difficult to do this inheritance stuff. Let's find a looser coupling. Let's invent type classes. And there you go back to the full wheel of functional programming. So I think it's a delicate balance, but to just throw out OO is, I think, the wrong way to do it.
Okay, so Anders, we don't have to be afraid that we're going to throw out OO, but what is the next big thing that you kind of are attacking?
Well, I mean, let me sort of, as a meta comment, the thing I've worked on for all the years I've been doing this, like 25, 30 years, is making programmers more productive. I mean, and I think that's still going to be the theme. Now then there's sort of the local memes, like yes, concurrency is a big thing. It looks like a next big thing might be machine learning, which we don't, as programming language designers, do much for at all. In fact, I still struggle to understand sometimes what it is, and what underlies it.
Oh, you just give a few examples and you hit the button and your program is written for you.
There you go. Yeah. I think it's fascinating, too, to see how much the programming language landscape has changed over the last few years, and how much it continues to change, and the language that was devised to be cross-platform, Java, is really no longer cross-platform, and there's a new cross-platform player in town called JavaScript, and the type system went out with the bathwater, and now we we can all wonder about how we do medium to large-scale efficient development, and so there's lots of new work invented there, that we can all start to ponder. So.
But are you implying that you cannot write big programs in JavaScript, or?
No, I think you can, but I don't think you can maintain them. I mean, like, try to refactor in a big JavaScript code base. I mean, is this X the same as that X over there? I'm afraid I couldn't tell you. So you can either change all of them or none of them. So I think there's definitely some unmet needs there. But and we'll see how that all shakes out. It'll be interesting. So the next few years it'll be an interesting ride.
So Gilad, what do you believe that you cannot write or maintain big JavaScript programs, and is that why you're doing Dart?
That's part of why we're doing Dart. Yeah, I think you can write them. It's terribly hard, and then after that you'll be suitably punished. But that is part of why we're writing Dart or doing Dart, is to make it easier for people to do what's called web programming, which to me is basically distributed programming in some form. Right? There's far too much mechanics of the web specifically that pollute this thing, that make this gratuitously hard, that need to be, we should try and get back to, say, let's not be too ambitious, but say 1995 or so, where there are real libraries.
Windows 95, do you mean that?
18.
Oh, 1895, okay.
So, right, we want decent libraries, decent abstractions. We don't want to worry about the quirks of this document format that has sort of, accidentally taken over the world. It's there, there's enormous value in it, but it needs to be utilized more intelligently.
But if you look at JavaScript per se, right, that is kind of defined completely independently of HTML. If that was the document format that you mentioned, or maybe you
that's true. So combining two bad things usually does not make them better.
So they don't cancel.
Unfortunately.
But then let me ask you the other question is, like, how much of, like, because if I look at Dart, and then it has beautiful libraries, but are they kind of really targeted towards cloud programming or distributed programming, or what is in Dart specifically for this?
Beautiful libraries, truth in advertising. It will, we promise, and you have to trust us. You will trust us. You will trust me. But I think they're targeted at the tasks that people do today and that we expect them to do in the future, more substantial tasks than they do today, that involve web programming, which means distributed programming. Typically, there is something out there on the server, something you need to do. There's a lot of stuff you can do on the client, probably a lot more than you usually do today, and you have to be cognizant of things like offline use and things like that, which the platform can make a lot easier. All of that has to happen, and no, it isn't there yet by any means, but we want, and as I said, the first step is to get back to 18 or 1995 or something, collections libraries, model view controller, just basic abstractions that are tolerable for programming these kind of client applications. That, we're not very ambitious. We just want to slightly civilize things.
So what is it with kind of programming languages and collection libraries? I mean, what is so hard about collections? I mean, why can't we just? By now that should be a solved problem, or not?
We need them because why else would we need generics? I mean, that's...
So Martin, there has been kind of a lot of comments about the kind of Scala libraries, where people say you need a PhD to kind of understand the types of like inserting into a collection. So this is your kind of chance to kind of
So yeah, I really have to say nothing could be further from the truth. So you can pick up Scala collections in half an hour. It will make you much more productive than anything else. It's precisely what Java wants with Java 8. So essentially we have it all today. And the point is, so the thing that gets me so upset is that we made a really big breakthrough in Scala, that we could have this amazing ease of use in purely functional collections. And we did it with some pretty clever types, but the users never see the types. So the types are essentially hidden. In other languages, you would have primitive collections in the language. It would all be compiler stuff. So you don't complain that language X has super complicated collections because you looked at the compiler and oh my God, how hard was it to implement that? Scala is like that. It's just out in the libraries, but essentially there are implicit parameters that get synthesized by the runtime that you shouldn't be concerned about even. You just call map and filter and it all works out beautifully with exactly the right type and things like that. And we are the only languages where actually it does work out exactly with the right type. So let me give you an example. So if you do filter over a set, what do you expect you get back? An IEnumerable or a set? I would say you should get back a set. If you get filter over a parallel set, you should get back a parallel set. If you do it over a sequence, you should get back a sequence. So Scala is the only language, the only statically typed language out there that provides this basic principle. The other language out there that actually can do it is Smalltalk, but that's dynamically typed with species. All the others, they have some fixed types and everything falls into these types, which I think is precisely the wrong way. So we worked very hard to get the right way, and now everybody says, oh, you need a PhD to use it, which is exactly the opposite from the truth, because that we did to make it easier, not harder.
So Anders, I can remember in the C# design meetings, you often kind of, say, oh, people will decompile or look at the generated code, for example, when we did like anonymous types and so on. And so in C# often we were very careful to kind of, to anticipate that users would kind of look at the kind of code that's get generated. Can you explain a little bit about about what your concerns are there?
Well, I mean, you can't, the magic can't ever get too non-transparent, and then people won't trust the code that gets generated. I think is sort of a reasonable starting principle. I was a little curious about what you said there about sets should return sets and whatever, but I suppose that's true if you're dealing with purely functional data structures. I mean, if they're mutable, then all of a sudden you can observe where they get, materialized and whatever. So, I mean,
so the whole thing is an artifact of saying we want to be functional, and then these things start to matter.
Sure, and it's true that if you say you want to be purely functional for everything, then things change dramatically. I think the trick is getting there, and having any semblance of performance left, at the destination. I mean, that really does still seem to be a challenge. I mean, but yeah.
But what is it with us developers that sometimes sometimes we are happy that, the hood stays closed and we don't have to look at the engine, but sometimes we look at it and we get really upset. For example, when Dart first came out with the Hello World, and people looked at the JavaScript, that baffled me because, whoever goes and looks at the assembly code that the C compiler generates, maybe, very few people, but they don't get too upset about it. So,
well,
what
the
is
real
that?
answer to all this is read something like Kahneman, the Nobel Prize winner in behavioral economics, who explains that the assumption of a rational agent in human affairs is fictitious. And that really is the root of all this. But to narrow it down a little bit towards your question, right? It's true. Why should they do? They do not look at generated code, but that's for two reasons. One is the main reason they've just been trained not to, and it's hard to look at the code, right? If it's too easy, if it's in a human-readable format, that they're like rats, they snoop and look, right? And so they will do it if they can. And the other reason is, of course, when it's a new tool chain, they don't trust it, and they have reason. There aren't good tools for debugging it, and so forth. Then, of course, they also make many naive assumptions. You show them a first-generation compiler, and it generates too much code. And since they have nothing more meaningful to say, they say, oh, it's too much code. And, gee, don't you think we know that? But it will change over time. And the code, there's actually a conscious effort to make the code somewhat readable in these situations, but you can't bank on that, and in some cases it won't be, right? And in principle, you shouldn't care. But they do care. What can you do? Brain surgery? I don't know what the answer is.
Yeah. So I often feel it's like, you give somebody $10 and they say, well, no, I want 20. It's like, why aren't we happy with, when I give you $10? But anyway, to go back to collections. So you mentioned, Peter, that, you when you have sets, they're easy to distribute and so on. Is that your main data structure, sets, because they have nice properties, or do you have other structures that, for example, maintain some kind of order over time, or?
Yeah, I would like to say that sets are the only data structure that we have, and that we sort of reified all the relevant state that you might want to be able to compute over on various different levels into sets. Because of this monotonicity, non-monotonicity issue that I mentioned earlier, we have abstracted a little bit from sets and allow programmers to basically express their computation, their collections as elements of certain lattices that have nice monotonicity properties, right? So the sort of driving example was actually
a lattice is not something that's in my shoes, right?
No, a lattice
or that I eat with with dressing.
It's an algebraic data structure. Okay. Particularly the kind of lattice that we're interested in is joined semi-lattices. We care about any two elements having a least upper bound because intuitively, imagine I have a distributed system and I have conflicting updates on different nodes, and I want to be able to know if I can always merge those updates. If all the possible collections that could exist at the different nodes are elements of a joined semi-lattice, then I know that there is always a least upper bound that I can find. The driving example was exactly aggregates, where you give a sort of a program that computes a count, or let's say a maximum of some set of integers. There's this intuitive monotonicity property that if I don't delete from the set and I'm only putting positive integers into it, that it's always growing. But if I do a sort of logic programming monotonicity analysis of that, I see this aggregate value being posited and retracted and posited and retracted. So we have abstracted a little bit from this sort of flat collections that have all these nice properties into more abstract data structures. At some level, I would like to be able to argue that they too are just collections, and collections is the right way to think about a uniform representation of state, because as you say, we can do nice things like just think about a partitioning and a replication of those collections being the topology of our distributed system, which is a nice abstraction.
So one thing that always makes me nervous about sets is that it assumes that you can compare, or that you can test two elements for equality. Whereas, if you go and do functional programming, if you give me two functions, good luck to tell me that they are the same or that they're equal. So how do you deal with that?
I'm afraid, Eric, I don't have a good answer for that at this time. We haven't had the need to pack functions into the fields of the tuples that we've shipped around in our system yet.
Oh, you don't have you don't have actors yet?
But you're absolutely right that, well, we have other ways of expressing partial computation and continuation passing that is not exactly higher order functions. And I suspect that as the language gets more mature and more people use it, we're going to have to face this issue. You're absolutely right that we assume that any two atoms in our universe can be compared.
So so now I like to kind of, because I've been kind of messing around with data structures recently, and there's so much work that's going on, but still I couldn't find the data structures that I wanted. So let me ask you, Martin. So one of the things that I wanted to do is I want to have a functional kind of data structure where I can do updates, but then I want to take a snapshot. So I say I have a sorted set, and I want to kind of add or remove something, but then I want to kind of take a snapshot that that contains the previous version without making a real copy. Is that something that your collections library supports, or do you say, Eric, if you need that, then something is wrong with you?
So you say you want to have mutable updates, so you want to mutate the structure and then you want to take snapshots.
Yes.
Okay, yeah, concurrent try, yeah.
Yeah, okay, good. Yeah. So maybe I should switch to Scala.
In Scala 2.10, we have concurrent tries. Yeah.
So Anders, do you think that we need those, like, if we go to kind of, look at concurrency and so on, do you think that there's a need for more kind of, advanced data structures like that?
I mean, absolutely, functional data structures are, I think, very, very useful. I mean, a project that we're working on currently is this project called Rosalind, which is the rewrite of the C# and VB compilers in managed code, and they are internally now entirely based on functional data structures, which means all symbol tables, all the ASTs, parse trees, etc., are immutable structures, and the only way you can make new ones is by making whole new trees. Mm-hmm. But of course, they reuse 99.9% of the old tree underneath the covers, and so you get the illusion that a new tree was created, but in reality, only very little memory was consumed by the operation. And the whole trick is like making these data structures performant enough. And that is a challenge. And often, for a lot of programs, it doesn't matter. But if in the limit, the difference is 2x or 3x, then for classes of programs, it will matter. And that's sort of what I was alluding to, you can go further and further with functional, but there's always going to be that ultimate imperative nirvana, for those who dare, right? But
you always need Jensen, And so Gilad is like, you said, you want to have like nice collection libraries. So one of the things that, I really, and I'm honest about this because I've been trying to kind of, convince Andrew Kennedy here, one of the guys behind C# generics or CLR generics, that we need unsafe covariance. Normal people, somebody had talked about brain power. My brain is kind of the size of a peanut. I don't understand this contra and covariance. So that's what I really like, that, Dart collections are just covariance. That's what I can understand, A list of students is a subtype of a list of people. So can you explain a little bit about the rationale for doing that?
Yeah, we wanted to endear ourselves to the type theoretical community. Basically, you pretty much characterized it. I've done generics more times than I care to admit, and we basically, this was a conclusion that was reached on the Dart team before I joined it anyway, but, explaining this stuff to ordinary people doesn't work. And we are tired of spending our time doing that. And so basically, it is more important that people are comfortable with what they're dealing with than that they understand things like contravariance and monads and all kinds of good stuff, right? We are after a very broad audience, which is not going to come to your terms. And so we basically decided that we're building a dynamic language. We have, for various reasons, there is some utility to types. It's just generally overstated. And so we have this optional type system. And optional type system is actually a thing that, to my surprise, I gave a talk once at Fool where I I foisted this idea on them, and they actually liked it. But and so we went a step further to up the game and made it an unsound optional type system. And that's really, that's when we hit pay dirt and we got this rebellion on. But it has the advantage that for every type theorist, there are probably 10,000 web programmers out there that thank us for it. And it's just simpler. And yes, it's not sound. We have mechanism for checking things dynamically with assertions, whatever. We have various tools. The point is, people are not there to serve the type system. The type system, or quote system in quotes, because it isn't a real type system, but the mechanism, it's a tool there that serves the people. And if it's unsound, that's just fine.
I think there's actually, there has been a shift over the last couple of decades of, the purpose of what we most appreciate type systems for. It used to be that type systems were the way that we got performance, and compilers could do smart things because they knew the types of these things. But more and more, if you look at what it is that we derive benefit from on a day-to-day basis, I think it's the tooling that you can build over type systems. When you know types, you can build refactorings that work, find all references, all sorts of pragmatic, IntelliSense, statement completion, things that if you take that away, people are completely lost. Like to the point of like deer in the headlight kind of looks. You mean I press dot and nothing happens? How can I program? And so.
Yes, and that's why I paid $25 for LinkPad to get that dot to work. Yes,
but it's really interesting because people will probably actually live with type systems that don't provide the absolute guarantees, because that's not really where the bang for the buck is at. The bang for the buck is more likely in give me tools that allow me to be productive. Do you know what I mean? And don't waste my time with these type theoretical.
So Martin, do you think that optional type systems would be better?
I'm not trying to sing Jalad's song here. I have.
Well, it sounded like it.
No, we can have a discussion about Dart versus JavaScript. That's a whole different discussion. But I do think that there has been sort of this cognitive change.
But isn't isn't having an optional type system gives you exactly enough to do what you want without kind of polluting the
Sure.
VM and everything with kind of types?
Sure, but do you need a new language to get it? So that's the question, right? Anyway, yeah.
So obviously I have to contradict now. So I think the importance is that you have the types work smoothly, and in particular work smoothly for the user. And so in my experience, there are many, many tens of thousands Scala programmers, and they do not have a problem with variants as consumers of libraries. It just doesn't exist. And why is that the case? Because a lot of work has gone into polishing the libraries that the variance works out correctly. And absolutely essential for that is to have, for instance, function types be contravariant in their parameters. If they weren't, at the use side, you would get lots of things which just wouldn't make any sense at all. So I think what being an unsound type system is essentially saying, well, let's not think too hard about these things, and let's just everybody happy with sort of half-truths about types. Whereas what
sounds like a winning formula.
Yes,
what we try to do is to say, well, library designers have to think extra hard to make things extra easy for the users. Now, there's one point. Well, there are 2 points. One is variance is probably the hardest part of type systems, and the other really annoying point is that normally with static typing, you have an escape hatch. It's called a cast. So if the types don't work out, just put a cast in.
Yes, or use reflection or whatever.
Right. In normal languages, you don't have a cast for variance problems. It just says, well, this won't compile. There's nothing you can do about it except completely rewrite your program. So one tiny small thing that we do have in Scala, and that I admit we actually used at a couple of points in the collections, is an annotation which says unchecked variance. So you can put that on a type parameter and says, believe me, this is going to be okay.
Unsafe perform IO is my favorite Haskell function too.
I really think types are good, but you always need the escape hatch.
So Anders, why are arrays in .NET still covariant unsafe? They are unsafe too, right?
Sure.
Why didn't you kind of change that when you did generics?
Right, because there's no point in breaking people's code for correctness.
But that code was broken in the first place, right? Because it's unsafe.
No, I mean, well, so the yeah, okay, but how often do people actually run into it? I do agree that it is a bit of an invented problem, but it's true that people do tend to think about things in covariant terms, especially when it comes to collections, and I suppose that's because they mostly think of reading things from collections where covariance is indeed true, and they forget about putting stuff into collections, and so in a functional world, you actually can have a covariant view of your collections because you're creating new collections every time. But the minute you're imperative, you again get punished. And now you can either choose to have compile time invariance, or you can choose to have runtime dynamic type checks, and you go pick your poison. I mean, I don't know that either is I mean, for historical reasons, we have dynamic runtime checks on arrays. We can optimize them out in cases where we know that it's an array of a sealed type or a value type, because we know there won't be any further variance here. And that means, like, for arrays of structs, we actually don't pay a price. And then it turns out, day to day, this isn't an issue in .NET. And therefore, why fix it if it ain't broken? Or ain't broken enough, at least.
So there's a lot of people here, and I'm pretty sure that many of you have questions that you would like to ask here. So I would now turn over, to questions from the audience. Carl?
Yeah, I'm interested in the inconsistency robustness issue. Eric came to our colloquium down at Stanford, and he and I got into this ferocious argument with Mark Miller, right, which ended with an inconsistency. And when Gilad came to Stanford, and he was attacked by a member of the audience for the inconsistency of
verbally, I might add.
So in the olden days of AI, we had the neats versus the scruffies. Is this now coming to programming language land, where we have the neats versus the scruffies, where the scruffies say, let's just live with the inconsistencies, and the neat says, no, let's exterminate them.
Yes, Peter, because, in some sense, you are kind of, you take the purist view, right? You want everything to be nice and pure and consistent, and you're trying to kind of, do that. So what is your answer to this? Should we embrace, just the fact that things are inconsistent and break and go bad and are non-monotonic,
Yes. We, applying a closed world assumption is a nice way to make forward progress in life. But as systems become distributed and we interact with agents who we don't control and whose knowledge we can't quantify over, it's not possible to apply a closed world assumption. So reality is ugly. There's no other way to answer that. I guess I would, in spite of my sort of obvious bias towards clean systems that I can write queries over, I would fall among the scruffies.
Martin's going to resist.
So I actually, can I switch? I have a question about, so are we comfortable with this sort of static partitioning of users into users and library writers? Because it seemed like we were achieving a consensus that, well, users can only get their head around covariance. So, but that's cool because we have all these expert guys who write the libraries, and presumably there's this assumption that you only have to write so many libraries, or the rate at which you need to add new libraries is smaller. But it's worrisome to me because we said the same thing at the advent of cloud and multi-core about parallelism generally, right? That, well, it's not a big deal. We'll relegate it to the library writers because those guys are smart, and those guys know how to write correct, distributed, consistent code. And it seems like in the last few years we've sort of just accepted the fact that everybody has to be a distributed and parallel programmer. And it's certainly the case, at least at a superficial level, that all users are library writers because they have to create abstractions and use their own abstractions. So are we completely comfortable? Certainly it's not a static partitioning.
That is actually a good question. So, like Anders, do you think that there's kind of the elite that kind of defines the libraries, and then there's the kind of the masses that consume them, or should we should everybody have like their own GitHub repository?
I think generally, it's a problem if the elite speaks a different language than their consumers, right? I mean, so ideally, you all reason in the same system of reasoning, or else you will have impedance mismatches, and then that leads to misunderstandings and wrong usages patterns and whatever. So So I think you either have it, say covariance or contravariance or invariance, or you don't. But then if you do, then it's your job to teach everybody. And if you can't, then you probably shouldn't have it. You know. How's that for openers?
Yeah. I think Gilad is right again. I mean, I wrote about this before, but it's like, because the thing is like, would you rather teach this or to that many people, or just live with it and kind of do like, do you think, Gilad, could you teach,
Well, of course you can't, but the other comment I'd make is this mythical elite that you're talking about, the ones that write the libraries so that they're easy to use and they just work, there's a small problem that they don't exist. People make mistakes all the time, and then they put this out and it can't be fixed later. And so reducing the scope over which they can make these decisions, essentially disempowering them in some sense, is a good thing.
No, I think it's true.
That's why you need variance. Exactly. because variance is a big restriction on the library writer. Everything has to be variance correct so that the user can employ these libraries without any care whatsoever. So that's precisely the difference.
Somehow that isn't what I meant.
Let me say, like, from my perspective, I'm lazy, so I'm happy if there's like library writers that kind of are smarter than me, that kind of come up with all the kind of complicated data structures, and I'm happy to kind of just clickety click and kind of glue stuff together such that I can get my job done.
So I think, well, when we said libraries, I think what we all meant is highly reusable generic libraries, and in fact I believe that's true, that requires a lot of expertise and a lot of taste, and I've seen a lot of even smart people getting it wrong. So I agree with Gilad there that it's a very, very hard problem, comparable to actually designing languages. To design really reusable general libraries is just as hard as designing your language. So in that sense, yes, it is an elite, and probably an elite which is much smaller than we all like it to be.
So, hello, long time no see.
Actually, two, and he touched on one there that I was thinking another. First one, particularly when you're talking about libraries, none of you have touched on the fact that whatever language you like your library in, can another language call it? So you haven't touched on any of the language interoperability issues. The other is distributed computing, or as that concurrency moving to languages, seems to me, I guess I still have most of my hair. We had DC.
It's a little bit grayer now.
Yeah. We had DC in the early 90s. That never really solved our distributed computing problem. Why are we going to do any better moving those problems into our programming language?
Because now we have REST.
Well, can you summarize the question?
So two questions is like, first one is what about language interoperability? And the second one is, we tried to do this distributed programming kind of many times before. Why would it succeed now where it failed in the past?
But particularly moving those hard concepts now into language.
Sure, but sorry. So it's a little story. I went on a trip over to Microsoft's data center in Quincy a couple of months ago. And it was really the most fascinating takeaway from that was seeing the difference between 5 nines and 3 nines, which to me also is the difference between stateful and stateless programming. You go there and you look at it's this beautiful facility, like the first generation of the data center, right? Built to 5 nines with air handlers and 16 diesel generators.
Generators
and
are cool,
AC towers. Oh my God, they're like motors the size of this room, and 12 of them. I mean, it's just enormous. I mean, it's just, you can totally geek out on all of the technology there, right? But running it, like 2x power goes in and 1x power gets used by the computers, right? And then you go down the line, and then you get to generation 4, which, by the way, is over on the corner in a shed, and they didn't even care to build a roof over it, and they've just parked some containers over there and piped some water into them, and that's it. And it fails as often as your computer at home, if not more. But it's fine, because they just roll it over to the other container or the other, and as long as your app is stateless, great. And they get to like, at least when it's not in in summer where they have to sometimes, but they run them all the way up to like 80, 90 Fahrenheit, within the specs of the boxes. And then, so in fall and spring and whatever, they don't even have to run AC on any of this stuff.
But
and
right now, you're talking about is fault tolerance. That has nothing to do with
no. But what I'm saying is just that one big learning here has been the switch from stateful to stateless, which again, like gets us down to functional programming and like these programming paradigms that, things have changed for distributed computing. And I think we have changed the way that we write these apps over the last 20 years dramatically. Well, maybe I misunderstood where you were going with it, but.
Maybe I can quick. So in fact, at least for Scala, it's not true that there are any distributed computing primitives in the language. It's all in the libraries, and I think that's the right way to do it. What you need in the language is the ability to essentially reduce state, and potentially what Scala doesn't do, but for instance Haskell does, is to control state and purity. And I think that might be the next frontier, that we are actually able to express that. But I think that's what we need to concentrate on, and not on getting some distribution primitives in there. The libraries do a perfectly good job.
Actually, I agree with that concept. Basically, good libraries for managing that complexity, but don't try to hide it. It will bite you.
So can I kind of, object? Oh, look at that, Jimi Hendrix. Because if we make, imagine that you want to build a shopping cart, right? That's the only thing we do on the web, is shopping. Your shopping cart is stateful. Imagine that, I buy new shoes, and then I click again, my shoes are gone, it's stateless. I want my shopping cart to be stateful. So aren't you kind of pushing the problem under the rug by forcing me to be stateless? And then somebody has to deal with the state.
Yes, but
but not you.
the state. It depends on where the state lives, right? If it lives on the client, it's not stateful on the server, and stateful on the server too could just mean there are patterns there you could use where you only write and you never modify, right? And then you clean it up occasionally, when there's low traffic or whatever. It's just different patterns, right?
So Peter, can you kind of, because the shopping cart is one of the sample codes that you kind of, have. Yes. Yeah.
So this isn't a complete, and I think your question is, why do we think, distributed systems, hard problem, well understood, why do we think that admitting distributed stuff into languages is going to make the problem simpler? I think it does, and this is only a partial answer to your question, but verification is one thing, right? If my language has primitives that talk about, this computation's results may be deferred to some unknown future time, which is really what distribution boils down to, right? I can't see certain information that is globally true, or I don't know when I'll see certain information that is globally true. A static analyzer can warn me about that. I can do global analysis of my distributed program. And in fact, although a language like Erlang, which is an actor-centric language, does have distributed primitives, a language like Erlang and the actor model, which is a really nice model for hiding the complexity of programming a distributed system, lacks, or I shouldn't say lacks, but it makes it a lot more difficult to do that sort of distributed verification of a global program, because you have to reason at the level of the actors about the correctness of the actors, and then you have to do this sort of other pass of reasoning compositionally about all the possible different interleavings of messages among these actors are going to have the right result. So
I found in my limited... wasn't that something like that? To prove, correctness of parallel programs?
So I think that I'm optimistic that languages where you can sort of describe the state of a distributed system moving over unsure boundaries over an unknown amount of time allows you to sort of get information back from a static analysis phase that says, as I'll discuss a little bit tomorrow, here are the places where you might be concerned about the consistency of the outputs of your system. So
I actually would like to have the opposite standpoint there, and that's that I believe we are way past the time where we could verify against essentially the language primitives. I mean, take collections. Almost no language has collections as a primitive, but to be able to do a good job verifying them, you have to essentially state your theorems on the level of the collection. So I think we need ways to abstract that we can have our verification conditions on the level of libraries, APIs anyway, and then it shouldn't matter again to actually put these things into a language.
We have a question here.
Hi, my name is Brian, and I play a library writer on TV. So
you're one of the 1%.
Yes, exactly. So I was very curious about what you guys thought about how we should go about writing better libraries that do work in this sort of world. And what tools are you going to give us in your languages? Do we need something like the ability to say this Lambda function has no side effects guaranteed? Or should we just end up giving up on a theoretically sound system and just sort of allow stuff to work and fail?
I don't know. So right now, I think in the world of effect checking, we're about where we were with Pascal in terms of static typing. That means we have systems, but they are clunky. They require you to go into quite a lot of contortions to express what you want to do. They don't have they're very rigid. You can't just essentially forget the rules in some part and then come back to the rules. So right now, I believe it's a very, very open question whether we will ever have these systems and how long it will take. I think it's something that is a very serious research problem, but right now I don't think there's anything out there that I would apply today. So right now I would be comfortable, or I would say probably the consensus opinion of most people would be to say let's treat this as a dynamic typing problem for the moment, but hopefully that will change in the future.
So if I may combine, these two questions, because you didn't answer that question about language interoperability, and if we combine this with distributed things, it's like when you're in a distributed world, you have to assume it's an open world, so you don't know, even if your program is typed, you're making a call to some other program. How do you know that program behaves, according to its types? So aren't all types vacuous in this distributed world? And have we assumed the worst, that, the other side can do whatever it wants and we cannot trust?
Hello? Well, I think interoperability between different languages, I think it actually these days is probably more a question of interoperability between platforms. I thought it was interesting to see the IKVM presentation. I found that fascinating. And now there's this other big player in town called JavaScript, which has a completely different object system, and then even trying to think about cheap ways of marshalling data between different GC environments and whatever. Well, no, but that's the expensive way of marshalling between them, right? Ideally, I would just hand the string pointer to the other guy over there, right? And I wouldn't have to, but which string is it? Yeah. And which object is it? And by the way, JavaScript's view of what objects are is very different and incompatible with how Java and C# views them. So there's some very interesting challenges there, I think.
All right, so one more question, I think. Andrew.
I guess I'd like to ask Martin what's so hard about effects. What's so hard about type systems for effects? It seems that effects are the real problem for concurrency, and we've spent 30 years doing these type systems for values, which we can perfectly well manage without, but they give us some benefits. But then the real problem is effects, and we're saying, oh, that's too hard. I mean, didn't we this, what's so hard about it, and why are we giving up on the problem that matters and spending all this effort on the problem that doesn't?
You never know in the end whether things will be hard or easy. I'm just saying I haven't seen one yet that I would personally feel comfortable using.
You don't like monads?
Not particularly, no. I think, for instance, what's wrong with monads is that if you go into a monad, you have to change your whole syntax from scratch. Every single line of your program changes if you get it in or out of a monad. They're not polymorphic, so it's really the old days of Pascal. So a monomorphic type system that says, well, that's all I do, and there's no way to abstract over things. So.